Hello everyone, I'm Pritima Samaniani representing Group 18. Today we are going to explain about the two research papers. The first research paper is based upon the mastering the game of Go with deep neural networks and research. So while coming to the introduction part of this, uh, the main uh, introduction part depends upon the game of Go and the NCTS search. Because of its large search space and the difficulty of judging both situations and moments, the game of Go has long been regarded as the most difficult of traditional games for artificial intelligence. This is one of the novel approach to computer science Go that evaluates both positions using value networks and selects move using some policy networks. This is one of the innovative combination of supervised learning from human expert games and reinforcement learning from self-play games is used to train these type of neural networks. Here we are going to use the optimal value function, which is defined with V star of S, which determines the output of the game is nothing but whenever it is used, the outcome of the game is determined by this value function. For example, for big games like chess, it is defined the value of B is 35 and the D is 80. And for the Go search, the value of B is 250 and the D is 150. It is impossible to do it with these kind of values, but we can reduce the values of B and D. On the other hand, we have another search like MCTS, which is also called as a Q learning. It starts off by randomly taking moves and we keep playing it until it finishes, like it depends upon the win or loss condition. The chance of making that move in the future is then adjusted by back propagating this information up the chain of moves. However, it isn't optimal Go because they are constrained by shallow policies plus value function. This is all about the introduction of this paper. While coming to the next part, supervised learning of policy networks. Here we can see two diagrams, which represents the first diagram represents the neural network training pipeline and architecture. And the second diagram represents the schematic representation of neural network architecture. The first stage of supervised learning, which uses a CNN method with ReLU activation. Here we have 13 layers and 13 million positions from the KGS Go server. The main purpose is to increase the likelihood of the correctly forecasting the following step. And the structure of RL policy network is identical to that of the SL policy network. Then we have our policy network play against a random sample of earlier generations of the model. At the end, when it was plotted against the old SL value, it won nearly 80% of that particular time. And when we plotted it against the best Go program, it came out on the top of 85 percentage of time, where a prior SOTA value is equals to about 11 percentage. So this is all about the supervised learning of policy networks. Well, coming to the next slide, which is based upon the reinforcement learning of policy networks. And these two diagram represents the strength and accuracy of policy and value networks. Uh, the main structure of RL policy network is identical to the SL policy network. Uh, the policy network play against a random sample of earlier generations of the model, which is used to stabilize learning and prevents our policy from becoming too like screen something. The reward comes in only at the end when we win or lose the game. After that, we train it to the maximum and the probability of winning. When it was pitted against the old SL value, it won nearly 80% of the time. And while coming to the next slide, which is a reinforcement learning of value networks, uh, here we can see the first diagram. Here we can see the policy network and the value network, and this by combining the state and probability distribution of these actions, the value network calculates the true value function, which is also known as the true probability of winning a given state. That's the value function for our most powerful RL policy, but we estimate it as well. The network has been designed as a policy, with the exception that we swap out the head for one with only one output. At the end, now all must do is train the value approximator on state outcome pairings in order to get it the minimized value. So this is about the reinforcement learning of the value networks. Well, coming to the other slide, which is searching with policy and value networks. Here we can see the three graphs A, B, and C. Alpha Go users most the research is a Monte Carlo research, which is in short represented as the MCTS. So many things are prohibited at the tree edge, like state action, action value, visit count, and the prior probability. Now, if we reach a leaf node with nothing below it, we can create a new leaf node. This is done by injecting the current state and the action into the SL policy network, resulting in a new state. We also keep track of this likelihood of it happening. So this is about the searching with the policy and the value networks. And the last is the evaluating the playing strength of the AlphaGo. So here we can see all the graphs with plotting some values like value network tree evaluation from value net, principal variation, percentage of simulations, tree evaluation from rollouts, and the policy network. First, we have it play a bunch of games with the other programs, and it destroys nearly 494 by 495, almost like a 99.8% win rate. AlphaGo is available in distributed version. Following that, we run this AlphaGo with various mixing parameter functions. The outcome of this is nearly greater than 95% of all other AlphaGo versions, implying that they both play a substantial role. So at the end, coming to the discussion part, the AlphaGo completed a job that was regraded as one of the machine learning major challenges. They achieved this by combining supervised and reinforcement learning in a novel form. At scale, these networks were integrated with the MCTS search, which is the powerful search. Furthermore, a Deep Blue used custom evaluation routines, whereas AlphaGo uses a general purpose SL value plus the RL value. These achievements paves the way for the possibility of opening doors in previously closed places. Plus, we can apply these concepts and methodologies to other fields of the machine learning. Till now, I have completed about uh, of the first research paper. The next research paper gonna explain by my teammates. Thank you.
Thank you, Pritma. Hi, this is Gautam. I'm going to explain about a second research paper that is mastering the game of Go without human knowledge. So here's the introduction. The game of Go has been long considered because of the maximum heart of conventional video games for its vast seek area and the problem of comparing board positions and moves. Here they introduce a brand new approach to computer Go that uses cost networks to assess the board positions and coverage networks to choose moves. So Go is a board game which could be very famous in massive element of Asia. It invented around 2005 years in the past in historical China, and few gamers have been committed their complete lifestyles to learning it. Even AI specialists believe Go might be unsolvable for a few many years because of its complexity, which originates from its Greek Seek area and the problem of comparing board positions and moves. Because of that, it ran into additionally taken into consideration as certainly considered one among the grand challenges of synthetic intelligence. These deep neural networks are um, skilled via way of means like a singular aggregate of supervisor gettings to know from human professional video games and reinforcement getting to know from video games to self-play. Uh, Next slide, please. So go here we can discuss about Go preference game. So the goal is here to surround more territory than the opponent. So if you see in the image, you can see two different color stones are there. So this game is invented long back ago, that is 2500 years ago. So players place like one player has white stone and other player will be taken the black stone. So there is a 19 by 19 grid on the board. So these stones cannot be moved unless a stone is fully surrounded by opposing players stones, which cause the stone to be removed. So at last, the player who has more number of stones in the board will be winning the game. Yeah. For developing these games, there are different methods they use. Two most commonly used methods are supervised learnings and reinforcement learnings, where supervised learning is nothing but create a policy network to imitate expert moves. With this policy, we can go at the advanced and mature level. Then we will let the policy network to play game with itself. So the best examples for this is AlphaGo Fan, AlphaGo Lee, and AlphaGo Master. Whereas for in reinforcement learning, it is a machine learning training method based on rewarding desired behaviors and punishing the undesired ones. In general, a reinforcement learning agent is able to perceive and interrupt its environments, take actions, and learn through its trial and error methods. So the best example is AlphaGo Zero. So, what is AlphaGo Zero? It was the first program to came out from the humans in Go. So, this AlphaGo program uses the combination of both machine learning and tree search algorithms. It makes use of a Monte Carlo tree guide through a free community and coverage community, each guide out the usage of deep neural network technology. So, by using this one, defeated the European champion in his name is Fan in 2015, and subsequent versions defeated world champion Lee Cyril in 2016. Um, so the AlphaGo is dedicated to imitate human play through trying to healthy the movements of the professional gamer from recorded historic video games and the usage of database of around 30 million movements. So to avoid desperately losing its opponent times, the system is particularly programmed to surrender if it's the evaluation of opportunity falls below a positive threshold. For the healthy in opposition to Lee, the resignation threshold changed into a set by 20%. So the architecture here they are following consists of two deep neural networks, a policy network that outputs move probability and a value network that outputs a position evaluation. So these are trained initially by supervised learnings to accurately predict expert moves and then refined by reinforcement learning self-play. Yeah, next slide, please. So AlphaGo Zero was trained slowly by self-playing reinforcement learning, starting with absolutely no knowledge, supervision, or human data. So this uses the neural community and takes uncooked board functions that represented with the different formulas in each scenarios. As its inputs, passes it via many conventional layers with parameters theta, and outputs each vector pt represents a possibility distribution over moves and a scalar cost vt representing the possibilities of the contemporary participating privilegation in the function. So these neural community parameters theta, which we can see in the diagram on the right, are up to date as a way to maximize the similarity of the coverage vector. So there are so many differences we can note in this AlphaGo Zero. The main three differences are: it reduces the input feature set. It only uses a single neural network rather than separate policy and value networks. It is much more simpler tree structure. No Monte Carlo rollouts are available here. So the network formula is defined here. F theta of S equal to P of V, where S is the input representation which we are passing to the post date and history, and P of V is the output one, where P is a vector of probabilities of selecting each move, and V is the scalar evolution that estimates the probability of the current player winning from the input position S. It consists of mainly two layers. One is batch normalization and rectifier non-linearities for calculating this output. Yep. Next slide. So coming to Monte Carlo tree search algorithm, so it is like a self-play simulation of the games. It starts from the root state that is initially the empty board. So these trees traverse by traveling along the edge that maximize the equation q of s comma a plus u of s comma a. These two are the main important parameters in calculating the Monte Carlo races, where q of s comma a is the action value for taking the action in states, also known as exploration factor, and U of S comma A is known as exploration factor that increases the changes of traversing that taking the new nodes. So U of S comma A is directly proportional to the prior probability of P of S comma A and inversely proportional to the count of the edge N of S comma A. So here in this Monte Carlo tree search, one leaf nodes is encoded means then the position is expanded or evaluated. Expanded is nothing but creating a new node that connect to yes, representing valid inputs moves that can be played from the board state, where evaluation passes the states into a neural network, which returns f theta of sp of b comma. This is the output we are getting. The probability vector of the state p is stored in each of the edges from the node. Finally, the value of this state is passed up the tree and updated into the q of s comma a value for each of the parent nodes with q of s comma a is the mean of all the child node values v. So the next part will be continued by teammate.
Thank you, Gautam. Hello, all. My name is Murali Krishnamurthy. So I'll be continuing from here. So we are going to discuss about empirical evaluation of AlphaGo Zero. In this diagram, so in the A, the performance of each MCTS player from each iteration of the reinforcement learning in AlphaGo Zero. Yellow ratings were computed from evaluation game between different players using 0.4 seconds of thinking time per move. For comparison, a similar player trained by supervised learning from human data using the KGS data sets also is also shown. Next one is prediction accuracy on human professional moves. The plot shows the accuracy of the neural network theta fi at each iteration of self-play. Next one is mean squared error of human professional game of outcomes. The plot shows the MSE of neural network theta fi at each iteration of self-play in predicting the outcome of human professional games from the Go Kifusi dataset. The MSE between the actual outcome and the neural network value we scaled by a factor of 1/4 to the range of 0 to 1. The MSE of a neural network trained by supervised learning is also shown here. So learning advanced flawlessly at all through preparing and didn't experience the ill effects of the motions or disastrous failing to remember that have been proposed in past writing. After 72 hours, we considered AlphaGo 0 in contrast to specific adaptation of AlphaGo Lee that crushed Lee Sedol under similar match conditions that were usually utilized in man-machine match in Sail. One self-learned player performed much better, generally speaking, overcoming the human prepared player inside the first 24 hours of preparing. So now we are going to discuss about comparison of neural network architectures in AlphaGo Zero and AlphaGo Leap. Comparison of neural network architecture using separate or combined policy and value networks and using either a conventional or a residual networks that combines dual res and separate SEPCON correspond to the neural network architecture using AlphaGo 0 and AlphaGo Li respectively. Each network was trained by a fixed data set generated by previous run of AlphaGo. Here in the A, each trained network was combined with AlphaGo 0's search to obtain a different player. ELO ratings were computed from evaluation frame between these different players. Next B is prediction accuracy on human professional moves for each network architecture. Next C is the MSC of human professional game outcomes for each network architecture. We thought about exhibition of the brain network design in AlphaGo 0 with that of AlphaGo Li. Four brain networks were made utilizing a fixed data set of self mess around. Utilizing a lingering work network was more precise, accomplished lower mistake, and further developed execution by more than 600 ELO. Joining strategy and work together into a solitary organization somewhat diminished the move expectation exactness, however, decreased the worth blunder. Now we are going to discuss about Go knowledge learned by AlphaGo Zero. So five human Joski discovered during AlphaGo Zero trade. The associated timestamps indicate the first time each sequence occurred, taking account of rotation and reflection during self-flip training. Extended data figure there too provides the frequency of uh, occurrence over training for each sequence. Five Joski flavored at different stages of self-play training. Each displayed corner sequence was played with the greatest frequency among all other sequences during an iteration of self-play training. The timestamp of iteration is indicated on the tablet. At a 10-hour, a weak corner move was preferred. At 47-hour, the 3-3 invasion was most frequently played. The Joski is also common in human professional play. However, AlphaGo Zero later discovered and preferred a new variation. Extended data figure 3 provides the frequency of occurrence over time for all five sequences and the new variation. In the C, the last 80 moves of three self-play games that were played at different stages of training using 1600 simulations per such. At 3 hour, the game focused greedy on capturing stones, much like a human beginner. At 19 hour, the game exhibits the fundamentals of life and death, influence and territory. At 70 hours, the game is remarkably balanced, involving multiple battles and a complicated fight, eventually resolving a half-point win for White Sea supplement. So here we can see visually like what I have explained right now. AlphaGo Zero discovered a remarkable level of Go knowledge during its self-play training process. This included not only fundamental elements of human Go knowledge, but also non-standard strategies beyond the scope of traditional knowledge. Figure 5 shows the timeline indicating when professional Joski were discovered. Uh, Ultimately, AlphaGo Zero preferred new Joski variants were previously known. Here we 5C shows several fast self-play games at different stages of training. Tournament length play games are played at regular intervals for training or showing extended data. Extended data. Uh, AlphaGo Zero rapidly progressed from entirely random moves towards a sophisticated understanding of Go concepts, including Fuski, Tesuji, Life and Death, Go, UC, Capture Races, Sente, Shape, Influence, and Territory. All discovered from first principles. Surprisingly, Shishiko that may span the whole of one of the first elements. Go knowledge learned by humans were only understood by AlphaGo Zero much later in the train. So here we are going to discuss about performance of AlphaGo Zero. So here, uh, he, uh, here Go program, Crazy Stone, Banshee, and Genugo. Each program was given 5 seconds of thinking time per move. AlphaGo Zero and AlphaGo Master played on a machine on the single machine on the Google Cloud. Google AlphaGo Fan and AlphaGo Live are distributed over many machines. The raw neural network from AlphaGo Zero is also included, which directly selects the move with maximum probability without using MCTS. Training started from completely random behavior and continued for approximately 40 days. Over the course of training, 29 million games of self-play were generated. We evaluated the fully trained AlphaGo Zero using an internal tournament against AlphaGo Fan, AlphaGo Lee, and several Go programs. We also played games against AlphaGo Master, which defeated the strongest human players 60-0 in online games in January 2017. So finally, coming to the conclusion, an unaltered, unadulterated support learning approach is completely plausible, even in most difficult of areas. It is feasible to prepare to godlike level without human models of direction, given no information on the space past fundamental guidelines in about a couple of days. AlphaGo Zero had option to rediscover quite a bit on this Go information as well as original techniques that give new experiences into the most seasoned of games. So that's it. Thank you all.
Thank you.